In this video, we're going to be learning about the chain rule. Once we've proven the theorem, we're going to use it to talk about implicit differentiation. The chain rule says that we have two functions, g that's differentiable at a, and f that's differentiable at g of a. And then it tells us something about the derivative of decomposition. It will be differentiable at a, and its derivative is going to be the derivative of f at g of a times g prime in a. The reason why we ask f to be differentiable at g of a, it's because we are here gonna evaluate the derivative of f at g of a. Another way we can write this is saying that f prime composed g evaluated in a times g prime in a. This is just another way you can see the chain rule. So let's go ahead and prove this. As always, when we want to calculate a derivative, we're going to be using the definition. So we're going to have to calculate the limit when h tends to 0 of f composed with g evaluated in a plus h minus f composed with g evaluated in a, and all these divided by h. So let's first use the definition of a composition. F composed with g is f of g of a plus h minus f of g of a, and all this divided by h. Here we should get to something with g prime, and for this we're gonna have to make this sort of appear here. So what we're gonna do is, this is equal to the limit of this thing, and instead of dividing by h, I'm just gonna write it like this. But now here, as I want g prime to appear, I'm gonna divide by g of a plus h minus g of a, and here I'm gonna multiply by the same thing. So I'm gonna write this fraction a bit differently, a bit better. And now I can use that the limit of the product is just the product of the limits. And now with this we know that this limit, because g is differentiable at a, this is very important. Because we know that, we can say that this limit will be equal to g prime in a, because it's just the definition of the derivative. But now here we did something weird, right? Because we never checked, we just divided by g of a plus h minus g of a. So this thing could actually be 0. And if it is 0, then we're in trouble. We're having sort of a problem here. And to solve this problem, we're gonna do this. Well, we'll define a function phi. We'll define it phi of h as this quotient, so f in g of a plus h minus f in g of a divided by g of a plus h minus g of a, and we'll define it like this. Whenever g of a plus h and g of a minus g of a is different to 0. And now let's check something. When we look at the theorem, we already have this. So now we need to obtain this other thing, the derivative of f evaluated in g of a. But if we check, when g of a plus h minus g of a is different to 0, then this fraction is very well defined. And when that happens, it is clear that this quotient tends to, when h tends to 0, to f prime in g of a. This, I'm not going to prove it because it's kind of intuitive. So what I do is I define this phi to be this quotient when g of a plus h minus g of a is different to 0, but when it is 0, I define it as f prime in g of a. And it's pretty obvious to see that phi of h is continuous at 0. So then what this is telling us is that the limit when h tends to 0 of phi of h is actually equal to f prime in g of a. So then if h is different to 0, then the limit of f of g in a plus h minus f of g in a divided by g in a plus h minus g in a times the other limit, because this is phi of h, then this is equal to saying the limit when h tends to 0 of phi of h times the limit when h tends to 0 of g in a plus h minus g in a divided by h. But now, here we said that this limit was g prime in a. And here we said that the limit of phi was f prime in g of a. So then this limit is just f prime in g of a times g prime in a. And that is the chain rule. So this is telling us that the derivative of the composition is going to be f prime composed with g in the point times g prime at that point. And this is the very well-known chain rule. So before continuing with implicit differentiation, let's have a look at two examples. In the first example, we're going to have to find the derivative of f of x equal to the sine of x squared. So when we see this function, we can differentiate two things. Here we have the sine of something. That's a function. But inside this, it's not just x, it's actually x squared. So then this is telling us that there is some sort of composition of two functions, call it h and g, in some x. And in this case, h of x is going to be the sine of x, because it's the function we are applying last. We take an x and first we are squaring it, and after doing that we are calculating the sine. So the last function we applied was the sine, and the first one was g of x equal to x squared. And now these two functions are differentiable at all the real numbers. So we won't have any problems there. Now let's find f prime in x. F is h composed with g. And so using the chain rule we just learned, we know that this will give us h prime in g of x times g prime in x. H of x is just the sine of x. So we have to first differentiate the sine of x and evaluate it at g of x. But then we know what g of x is. G of x, we said that was x squared. And then we have to multiply it by the derivative of g of x. So in our previous video we learned the derivative for the sine of x. We said it was the cosine of x. So now we have the cosine of x and evaluated it x squared, which just gives us the cosine of x squared, times the derivative of x squared. We calculated a few videos ago that it was 2x. So then we can just rewrite this as 2x cosine of x squared. So this is the derivative for our function f. Now we're going to move on to a bit more complicated of an example. Our function f of x is going to be quite long. It's going to be the sine to the power 3 of the sine squared of the sine of x. So now we start with this. The last function we're applying is the power 3, and we're applying this to everything. Then after this we had to calculate this sine. But after calculating this sine, we first had to square this function. We are squaring all this thing that's in here. After squaring, we had to calculate the sine of something. And we were actually calculating the sine of the sine of x. So we kind of have the order in which we are calculating our functions. So to make this more clear, we can write this as something to the power 3. That something is the sine of something. And in here we calculated something squared. And again, that something was the sine of. And that was the sine of x. So once we've written this like this, we kind of have our functions. We're going to have a function h composed with a function g composed with I composed with j, and finally composed with k. And this is all just evaluated in x. So first let's define these functions. The first one is h of x, and from our color code it's easy to see that h of x is x to the power 3. And then we have g of x equal to the sine of x. Then we have I of x. It's going to be x squared. And then j of x is the sine of x. And finally, k of x is also the sine of x. So let's see what if the derivative of x would look like. So to differentiate f, we have to first differentiate the last function we calculated, that is h prime, and evaluate it in all the previous things we had. So g composed with I, composed with j, composed with k in x. And now we take all this and we have to differentiate it. So multiplied by the derivative of g composed with I, with j, with k in x. But now we have this derivative, and again we have to use the chain rule. So we have this first term, and now for this one we first differentiate the first function, g, and evaluate it in all the rest. And then what we do is we take all this thing and we have to differentiate it. So we multiply it by the derivative of I composed with j, composed with k. So now we have these two products, and for this derivative, again, we first multiply by the first one, evaluate it in j composed with k, and then we multiply this by the derivative of what we had inside, so times j composed with k prime. So we have all these functions, and to differentiate this last one we multiply by j prime evaluated in k times the derivative of this, so times k prime in x. And then that was the last function, so we just stop there. So now we have to replace these functions here. We first have h prime evaluated in all this. So h prime is 3x squared. So we're gonna have to change this x with all these things here. So it is 3x squared. So 3 times something squared. And that something is going to be g composed with I, composed with j, composed with k. And that is exactly what we have here. Let me just make this a bit smaller. And this is this first term. Now we multiply this by g prime. G prime is the cosine of x. So we're gonna have the cosine of, and instead of x, we're gonna have all these things here, and that is exactly what's inside our function here. So again, multiplied by I prime is 2x, so we have 2 times something, and that something is going to be what's here, so it's going to be the sine of x. Now j prime is the cosine of x, so we're going to have the cosine of something, and that something is what's inside j in here, so it's the sine of x. And finally, we multiply all this by k prime, and k prime is the cosine of x. So then this is our derivative. We're going to have 3 times the sine of the sine squared of the sine of x times the cosine of sine squared of sine of x times 2 times the sine of the sine of x times the cosine of sine of x times the cosine of x. And now here we have a 3 and a 2. We can multiply those two together. And so we will have that this is equal to 6 times this whole thing, and this is f prime in x. It was a very long derivative, but the chain rule made it easy for us. Okay, so now we're gonna move on to implicit differentiation. And we're gonna learn this with an example. Let's say we have x squared plus y squared equals to r squared. From previous videos, you know that this is the equation of a circle with a radius of r. So the usual way of differentiating our function is saying, okay, y squared is equal to r squared minus x squared, then y is plus or minus the square root. And so here I have two functions. I have f of x equal to the positive, and I have g of x, the negative. So I can just differentiate each of these. F prime in x is the derivative of the square root. Here r is a number, it could be 9, 3, 1, not just any number. I'm just doing this for the general form of a circle. And now, if we remember that the square root of x is actually x to the 1/2, then the derivative of the square root of x is 1/2 times x to the minus 1/2, because it's 1/2 minus 1, and so this is 1/2 times the square root of x. So using this, we can calculate this derivative using the chain rule, because we have a square root and we have a function inside that it's multiplying x by minus 1 and squaring it. So this will give us the derivative of the square root of x is going to be 1/2 times the square root of whatever it's inside. So r squared minus x squared, and now times the derivative of what's inside, and that is minus x squared. So the derivative of minus x squared is minus 2x. And now I can just cancel out the 2's, and we get minus x over the square root of r squared minus x squared. But now this is our original function, so we get minus x over f of x. And now let's do the same thing with g prime. Now a bit faster because we already know the very basic derivatives. This is going to be minus 1 over 2 times the square root of x squared minus x squared multiplied by minus 2x. So now the minus signs and the 2 cancel out, and we have x over square root of r squared minus x squared. But now this is minus g, because g has this minus sign over there. So then we can just write this as minus x over g of x. So in essence, remembering that f of x was equal to y and g of x was equal to y, we know that y prime is minus x over y. But now this was very long and very complicated, and so we ask ourselves if there is another way to calculate these derivatives. And there is. That is using implicit differentiation. So again, we start with the equation. We had x squared plus y squared equal to r squared. And let's try and find the derivative for this. So the derivative of x squared is 2x plus, and here we're going to have the derivative of y squared, which we don't know how to calculate. And then this equals to the derivative of r squared. Remember, r is just any real number, so the derivative of a constant is 0. And so we have 2x plus, and here there's something we have to remember. Let's just call y is a function of x. So let's call it f. What we're actually calculating here is f of x squared, the derivative. So we are squaring a function. And this is our moment to use the chain rule. It's just what we just learned. So this is 2x plus, we have two functions, call it h equal to x squared, and well, g, that's going to be f. So then the derivative is going to be, the derivative of h is 2 times evaluated in f, in g. So g is f, so evaluated in f of x, and then times the derivative of g, which is going to be the derivative of f. And this has to be 0. So then we just said that y was equal to f of x. So we have 2x plus 2 times f, that's y, times f prime, that is y prime, equal to 0. So now let's isolate the y prime. We have y prime is equal to minus 2x divided by 2y. And now cancelling out the 2's, we get minus x over y. And this is y prime, that is exactly what we got here, but only way faster. And this was only using the chain rule, because as y is a function of x, then we can use the chain rule here to calculate its derivative faster.